Okay, so here we go. Last time we were talking about this theorem right here. And there's a lot to say about this theorem. I'm not going to repeat the whole thing, but I'm going to remind you there's a certain amount of setup that basically, given a list, you can create a matrix which defines a linear transformation, which defines a parallelogram, right? And then the theorem consists in observing some relationships between these various different things. In particular, the magnitude of the determinant tells you the area, right? Well, let me just leave it at that. And then the sign of the determinant. Now, this could be viewed as telling you a couple of different things. One interpretation you can make, let me go ahead and clean this up. One interpretation that you can make of the sign of the determinant is that it tells you whether this order is counterclockwise or clockwise, right? And that's a useful point of view sometimes. But very importantly, and I think arguably more importantly, I guess it depends on the context, you can view it as telling you something about the linear transformation itself, right? Not the vectors that come out of it, but what is the linear transformation itself doing? And in particular, we talked through the details last time, it tells you whether or not this linear transformation, among all the other things that it's doing, like rotating or stretching or shearing or what have you, is this linear transformation also flipping upside down, right? Is it turning things upside down, or is there a kind of a mirror imaging, a reflection, for example, involved somewhere inside? Now, closely related ideas. The reason this matters is because a function is what I'm going to call an active thing. Something's happening, right, with a function. Whereas if you're just looking at the pair of vectors and deciding if that's left-hand or right-hand order, they're just sitting there. There is no action. Nothing's happening there. So I think it's important to recognize these as two importantly different, both useful, but different points of view on ultimately the same thing. All right, now this is where we ended last time. There is a three-dimensional version of this theorem. As stated here, two vectors in R2 that makes a 2 by 2 matrix, which is a linear transformation in R2, making a two-dimensional parallelogram. So what do you suppose the three-dimensional version of the theorem is going to be? Well, here it is, and it's exactly what you would think. It's about 3 vectors in R3 that makes a 3 by 3 matrix, which defines a linear transformation in R3, which makes a 3-dimensional parallelepiped, they call it. It's kind of like a parallelogram, 3-dimensional. And the results are exactly what you would think. The determinant, specifically the magnitude, the absolute value of the determinant, it tells you how big is this thing. Now, okay, sure, to be fair, how big in 3 dimensions is a different idea than how big in 2 dimensions. When you're in 2 dimensions, how big means area. Here in 3 dimensions, how big means volume. Right? So a little bit different, appropriate to the context. Same basic idea, though. And then the sign of the determinant, again, it telling you something appropriately different to the context. It's telling you about the order of these output vectors, A, B, C. In 2 dimensions, that's clockwise versus counterclockwise. Here in 3 dimensions, it's right hand versus left hand. Right? That's, again, the sort of the static point of view on what the sign of the determinant's telling you. The different, kind of more active interpretation is that it's telling you about the transformation itself. And again, same idea. If this linear transformation turned the always right-hand order E1, E2, E3 into a different right-hand order ABC, well, right hand to right hand means that, there might have been a rotation or maybe a stretch, maybe a shear or something, but basically no reflections. Whereas on the other hand, if this determinant's negative, the idea then is that the right-hand order, always right-hand order E1, E2, E3, turns into a left-hand order ABC. And what can turn a right hand into a left hand? Well, it's got to be a reflection. There may be other things. There may be a magnification. There may be a stretch. There may be a shear, rotation, whatever. Fine, but there's a reflection in there somewhere. There's no way that I can rotate my right hand around and have it turn into a left hand. It just doesn't work. Does that make sense to everybody? All right, so that's the three-dimensional version of the theorem, morally equivalent theorem. Okay, moving on now. Make a definition. Talk about the cross product. Here it is. It's a formula, a notation and a formula. There it is. You will definitely need to know how to compute cross products. That said, I do not recommend that you memorize this formula. I never have. I've never needed it. And the reason is because there is a better formula to memorize to help you compute cross products. It's this thing right here, what I call a symbolic determinant. Now, I have to say it's a symbolic determinant. It looks like it's a determinant. It says determinant right there, right? But it's not really quite technically a determinant. After all, a determinant is something you do to a matrix. A matrix has entries that are numbers. This thing that I've written down here has entries, some of which are vectors and need to be vectors. So that this whole thing's a little squirrely. I mean, this looks like a matrix, but importantly, it's a little problematic as to whether it actually is. And can you really take a determinant of something if it's not even really a matrix? That's questionable as well. So let's not worry about whether that's legal. What's convenient about this is that if you ignore the question of legality and just compute that determinant symbolically as if this were meaningful, as if it was okay, even if it isn't, the formula you get is exactly the formula that you want. So, nice little shortcut. And again, in my life, I've never memorized this formula on the left. I've always operated on the basis of this formula on the right. So, that's what I would encourage for y'all. But everybody's different. Okay, weird formula. I guess I'll make a quick observation while I'm here. Let's kind of see how does this formula produce the formula on the left. Let's take the symbolic determinant. Let's get started taking the symbolic determinant. Top left, multiply by the determinant of the submatrix. And notice I get A2B3 minus A3B2 all multiplied by the E1 vector, which puts the correct entry in the first entry of the cross product. And then, moving along, E2 times the determinant of its submatrix. So I would have A1B3 minus A3B1. That gives me this correct second entry. Oh, don't forget your minus. Don't forget that whole plus minus plus thing when you take a determinant. And then likewise for the third entry. Right, so it just works. Okay. All right. Here's another formula that just kind of works out, and it's just kind of beautiful that everything fits together here. And that is this thing that I call, well, that is called the triple product. Oh yeah, question.
Can I ask something about the previous formula?
Yeah, sure. What's up?
So we just get rid of the E1, E2, E3 vectors?
No, we're not getting rid of them. It's just that, so again, if I write this down, I'm going to have, for example, let's see, A1B, no, sorry, oh man, I got the wrong, okay, A2B3 minus A3B2 times E1, right? But if you think about what E1 is 1, 0, 0. And then now, sure, plus other things, right? But altogether, this times the one that's in that first position is what puts that expression in the first position right there. Is everybody happy with that? Yeah. and then likewise for the second and third. Yeah. All right. Cool. So, so this other formula down here, the triple product formula, concerns this construction here where you take a dot product of a cross product. What an odd thing to want to do. So it would seem. We're going to play along just because something nice is about to happen. Dot product with a cross product. Now, real quick note. Yes, dot products are commutative. You can write the dot product on either side. It doesn't matter. But that said, you're going to confuse yourself if you kind of write things down in different orders when in some other context you can't write them down in different orders. I strongly advise just to keep things simple. Always write your triple product with the dot product on the left, your cross product on the right. Again, not that you have to, but I don't think there's much to be gained by doing it the other way. Okay, that said, we have a formula for our cross product. There it is. Dot product. How do I dot product with some vector C? Well, okay, I'm going to multiply, multiply and add in the usual way. And now let's just start writing stuff down and see what happens. For example, if I multiply it as per this dot product, C1 times all of that business, notice that's the first entry in this determinant over here, C1 times that little submatrix determinant. And then likewise for the remaining terms. If you go down this dot product, first term, second term, third term, what you will find is that you get exactly the three terms that make up the determinant of this little 3x3 matrix here. It's just I'm going to call it a coincidence, but it's a wonderful, let's call it a coincidence, depending on how you look at it. So nice fact, and the altogether punchline is that the triple product is a determinant. All right, the reason we care about this is because this connects some ideas in an important way, specifically the cross product that I've just now written down a definition for. I don't really know anything about the cross product yet. It's a formula. It's a weird formula. Okay? Now I know a connection between that mysterious object and the dot product that I already understand pretty well, and the determinant, which we already understand pretty well. And so this is a nice foot in the door for helping us to understand about the cross product. Everybody see the potential, at least, for that to bear out? Okay. All right. So, first fact. Real quick, I did say previously that you're not responsible for the proofs. I'm going to, in this section that is, I'm going to talk about the theorems, and then you don't have to know these proofs. This is not I'm not going to spend class time on it, but you're still responsible for it anyway. This is I'm not going to spend class time on it, and I don't feel in good conscience I can still make you obligated to understand the harder reasoning, and so we're just going to remove it entirely. Okay. All right. That said, I am going to make a quick comment about this one, starting first, of course, with the statement. The statement here, if you have a cross product that is always orthogonal to both of the input vectors A and B. Always orthogonal to both of the input vectors. Very cool fact. By the way, already pretty persuasive that weird formula we wrote down is must be natural somehow, because orthogonality, perpendicularity, very geometrically natural idea. Right? So we've got, okay, fair, a weirdo formula, and yet it's geometrically natural in this pretty persuasive, pretty strong way, I think. All right. Okay. Now, let me show you a proof of this. Orthogonal means that we're going to compute a dot product and our answer is going to equal to 0. That's what orthogonal means. Now let's talk about how to compute that dot product, and you could brute force it, I suppose, but we're going to do something more clever. This dot product that I need to compute, very importantly, check it out. It is not just any old random dot product. It happens to be exactly the triple product. And as we saw above, triple products are determinants. Determinants we understand. Determinants, for example, determinants give you volumes. Well, the absolute value gives you volume. And I can just straight up look at these three vectors, A, and B. Now again, that's just following the rule. First vector, second vector, third vector. Make those the rows. Three vectors, two of which are exactly the same vector. This is not this kind of a situation where we have three vectors pointing three different ways. I have two of the three are pointing they're exactly the same vector. How much volume does this make? It doesn't. There's 0 volume inside of here. Right? This is as I like to call it, this is a cardboard box that has been smushed for recycling. There is no volume left. And no volume means the determinant is 0, which means the triple product is 0, which means the dot product is 0, and dot product equals 0 means orthogonal. Okay, now so I wanted to go through this one argument here because I wanted you to see how the triple product helps us so valuably in being able to take a question involving cross products and how we can use our knowledge of dot products and our knowledge of determinants to then draw a conclusion about cross products. And this argument does that. So as promised, that triple product formula, very cool, very useful. Everybody okay? And that's the last proof that I'm going to do in this section about cross products. Okay. All right. So make sure to know the facts, though, and in particular, cross product, orthogonal to both of the inputs. Fine. Moving along. Triple products are preserved by cycling. Cycling, you'll recall, means that we kind of move everything over by one notch, and then when you fall off of the one side, you reappear back on the other side. So if you cycle the list, and again, keep in mind, just to avoid problems and confusion and stuff, I'm always going to write my dot product on the left, cross product on the right. Again, it's not that you have to, it's just that it makes things a lot weirder and harder to keep track of patterns if you don't follow this rule. So that said, triple products, dot product on the left, cycling preserves triple products. Now, reminder, even though you're not responsible for this proof, and I'm going to exercise self-restraint, I'm not going to actually talk through this proof, I do want to remind you, they are still pretty cool ideas. These ideas may help you develop an intuition for cross products and triple products and determinants and etc. Right? So I encourage you to take a look at these proofs. You don't have to, and you're not responsible for it. Okay, but you do need to know this fact: cycling preserves triple products. Here's the next one. Same story. Cool proof. You're not responsible for it. I encourage you to take a look. You don't have to. All right, so what does this one conclude? This doesn't quite fit on one screen, so let me do this. This says that if you have a cross product and look at the magnitude of that cross product, what you get is the area of the corresponding parallelogram. So, neat fact. Two vectors define a parallelogram. Same two vectors, you can make a cross product. That length equals that area. Kind of want Yeah, so make sure you know that fact. And if you're looking for an exercise, a little bit of mathematical weightlifting to help you understand the ideas a little bit more, then this argument is lovely. Give it a look, but you don't have to. I hope you'll find it interesting. Okay, is everybody happy? Okay. All right. Moving along. Let's see here. Let me zoom back in. In the same way that a dot product being 0 means something, a cross product being 0 means something. In this case, that list of vectors is linearly dependent. So, different than if the dot product is equal to 0, but still pretty cool. Again, know the fact. Again, this is a pretty clever little argument, and it's a nice little exercise to think about. You don't have to. I hope you will. All right. Next fact. This list here, in the order as written, do be careful about this. A first, B second, cross product third. And furthermore, the first vector that you list is the first or left vector in the cross product. The second vector that you list is the second or right entry in the cross product. All that business is very important, right? So that list, written exactly so, loosely speaking, is always in right-hand order. Loosely speaking, and now I have to correct myself. Technically, it is possible that one of those vectors is 0 or something, in which case it's not either right-hand or left-hand order. So technically, it might not be in right-hand order. But what it is, it's never in left-hand order. This is 100% accurate, never in left-hand order. And so you can see why we'd like to say what's right-hand order. But, again, you've got to worry about the little anomalies. Okay, neat fact. Again, cool proof. Take a look if you like. You don't have to. Pausing. Questions? Okay. Yeah.
Just had one about triple product. So,
yeah.
Is there ever, do we always refer to triple product as the dot product of a cross product? Can you have two cross products?
No, I hear you. No, it's specifically a dot product with a cross product. Yeah, it's that exact construction. Let's see here. Yeah. Eraser now. Yeah, triple product always means exactly that. Yep. Good question. Anybody else? Yep.
On that last one you did, can you say what the order was again?
Oh, this one here?
Yes.
Yeah. So, first vector, second vector. Let's see here. Let me do it like this. First vector, second vector, and then the third vector is first cross second, specifically.
Okay.
Right? So, green, blue, orange, and orange has to be green cross blue. Yeah. Everybody happy? All right. Okay. Yeah, again, cool proof. Take a look. You don't have to. Let's see here. So this gives us what I like to call a purely geometric description of the cross product. When you're talking about the cross product, sometimes a formula is what you want, right? But on the other hand, sometimes it's good to know how to talk about the cross product, without getting bogged down in formulas. Geometrically speaking, what is a cross product, right? And very nice point of view is it's the unique vector that has these three properties. And I claim this, again, purely geometric. Notice perpendicularity. It's a purely geometric concept. Area, purely geometric concept. Order, being, left-handed or right-handed or what have you, purely geometric concept, right? So, geometric description of the cross product. In fact, you can use this as an alternative definition. You can define, as the book does, that the cross product is the unique vector that satisfies all three of these conditions. And what the book does, it's really a very nice point of view. They take this geometric characterization and then they start working out the formulas, and their punchline is the formula that we started with. So Kali likes to just kind of take those ideas and kind of do them in the other order. I like my way better. Again, I think it's more geometric. I think these proofs in here that I've left off, but like this argument right here, much more sort of geometrically satisfying and picture-oriented and, I don't know, better for intuition, in my opinion. Kali's take, I think if you look at it, you'll find it's pretty algebra-heavy and pretty, I think, cryptic, hard to get a sort of intuition for. Different strokes. Her approach has some advantages as well. Okay. Okay, let's see here. A couple more things to say about the cross product. It's not commutative. Watch out for this minus sign. Now, we're accustomed, in most cases at least, that multiplication is commutative, right? I mean, 3 times 2 is equal to 2 times 3. You get used to that. When you do algebra, sort of high school algebra, you kind of move factors around willy-nilly, whatever seems convenient. If you're too accustomed to that, you might accidentally just too quickly, too carelessly change sides of the vector in a cross product, and that doesn't work. Cross product is not commutative. Good news, it is anti-commutative. All you got to do is put a minus sign in there, but you do have to remember that minus sign. Okay. All right, and then the last couple of properties here. This first one we've talked about previously. I left this as kind of an exercise for y'all to work out on your own. I made the observation that if you fix some vector A, cross product with the vector A can be thought of as a function in the sense that whatever vector you give me, I'm just going to cross that with A. That defines a function, and that function, previously discussed, is linear. So all I'm going to do here is flesh out what that looks like. And so keeping in mind, here you go, cross product with A, cross product with A, cross product with A, and keeping in mind that that's what T is. So that's just the action of T. That's T, and that's T. And notice what this is saying then is that if I have a sum of scalar multiples of vectors that goes into the function T, the result is the sum of the same scalar multiples of what comes out of T. So this is literally just right down the pipe exactly what the word linear means for that function. Is that cool? All right. Okay. Right. Now, I claim it's not hard to show if you do the cross product with the fixed vector A on the right hand side instead of the left hand side, it defines a different function. It is still linear. It's a different function, but it is still linear, and this is what that looks like. And again, nice little exercise to think through. How would you interpret this as a statement about linearity of T? Again, nice little practice problem. Okay. Alrighty then. Last comment about properties of cross product. Again, this is more of a landmine observation. Again, the cross product's not commutative. Do be careful about that. It's easy to mess that up. Likewise, it's not associative. And by the way, it's not even close. With commutativity, cross product is, well, it's not commutative, but it is anti-commutative. It's one minus sign away from being commutative, right? So it was kind of close in a way. Just not associative or anything even vaguely. It's not anti-associative. It's just not. It's nothing. So another landmine. Don't make the mistake of too casually moving parentheses around or anything like that. Okay. All right. real quick, some applications. This is not a physics class, but I do think it's worthwhile to at least point out the ways that cross product shows up in the physical world, because I don't want you all to think cross product is just a made up nonsense that mathematicians play with, right? This has real context. In particular, torque, the idea of if you have a bolt that you want to unscrew and you put in your wrench or whatever and you turn, right? The idea of torque is that there is a notion of how hard you're turning that doesn't depend only on the force that you apply, but how big is your wrench. And if you're used a substantial wrench to try to open, to unscrew a bolt, I'm sure you would have noticed as well that if you just grab it by your fingers, you forget about it. It's never going to come open, right? Because you're effectively your R here. How big is your wrench? It's too small, not enough torque, right? It's not about force; it's about torque. So this important and natural physical concept is a cross product, as it turns out. Here's another one, magnetic fields. Kind of weird, but if you have a magnetic field, like so, let's just say, and if you have a charged particle moving through that magnetic field with some velocity, the weird thing, and don't look for any intuition for why this is true, this is just empirically the way the world works. Nobody knows why. But there is a force that is created when a charged particle moves through a magnetic field, and the force is a cross product. Again, it just is. So again, physically natural, right? This cross product is not just made up nonsense to entertain mathematicians. It is a real physical, natural thing. Everybody okay? Everybody buy it? All right, so that does it for section 1.4. We move on now to 1.5. We're going to talk about equations of planes and related stuff. And here we go. Let's talk about the equation of a plane. Here's a plane. How am I going to write down the equation for that plane? I'm going to need to be more precise about what I mean by that plane. Specifically, what plane am I talking about? And there's different ways that I could precisely describe a plane. I'm going to, in this case, describe it by identifying a point on the plane and by identifying a vector perpendicular to the plane, and we call that a normal vector. Normal in this case just means perpendicular. Right. And I hope your geometric intuition is happy with the idea that normal vector kind of describes how that plane is oriented in space, right? And then once you tell me, and it's got to go through a given fixed point, well then there's only one plane that can go through a given point and be oriented in exactly the way as described by that normal vector. Everybody believe that? All right, so now we wanted the equation of the plane. Don't forget what an equation is. An equation is a test. We're not going to try to manufacture points in the plane. That's a totally different thing that we'll get to later. An equation is a test. So I need something that if somebody comes up and says, hey, there's a vector x, can you confirm, please, that vector is in the plane? Right? That point x is in the plane. How would we test that point? And the big idea is, if that point is in the plane, that would mean that this difference, if you think about it, this difference vector here starts in the plane and ends in the plane, which means that this difference vector is parallel to the plane. Yeah? And then, if that's parallel to the plane, keep in mind my n was perpendicular to the plane. That means that those two vectors would have to be orthogonal. Yeah, right, orthogonal. There we go. Dot product is 0. And that's the test. So this equation right here, keep in mind an equation is a test. Given an n, given an x0, this equation is something where I can plug in an x and see if the equation works or doesn't work. If the equation works, then the point is in the plane per my picture here. Everybody all right? Okay. All right. Cool. So now there's different ways to write this down. I like what we have here. That dot product is 0. Very cool. You can sort of multiply that out and move terms around. That's morally equivalent to this equation right here. Pros and cons. I do kind of like when there's a 0 on the right-hand side, right? But there is also something kind of appealing about the simplicity of this equation. The left side and the right side look very close to the same. Another way to say this is that all vectors x that are in the plane, they all give you the same dot product with n, just like x naught does. Right? That's a take that you can get out of this equation more so than that one. So it's a pro-con thing. They're both nice in their different ways. It's a good idea to be familiar with both of them. Okay. All right. Now this is what you might call a vector equation. Everything's written as vectors. That's useful in a lot of circumstances. But do notice sometimes we need things written in terms of coordinates. And after all, this point here, x, that I'm going to test, is going to come to me, or might come to me with literally coordinates. Let's say x, y, and z. So this x will have coordinates x, y, and z. This normal vector will have some coordinates. Let's call them a, b, c. And that allows us to rewrite our equation. This vector equation right here now turns into this sort of coordinate equation where everything in here is just a variable or just a constant. Yeah.
Well, so you're saying like the one in the gray box, that equation, and the one below essentially translate?
Yep.
Why is D not always 0? Because
Yeah. Okay, right. So you have to keep in mind that, let's see here. So this equation and this equation are two different ways of saying kind of the same thing. But if you want to say 0 here, then that would have, then, you'd need to take that instead of this. So you can't mix and match the.
right.
Yeah.
I thought the normal was perpendicular to the plane, and x naught is on the plane.
Right, but now you're conflating two ideas that don't conflate. So you got to remember. So points have locations, right? And if you want to talk about the location of something like x naught, it's a point, not a vector, and it doesn't have a direction, and you can't talk about it being parallel to anything. Right? Yeah. So the idea of parallelness, and what you see in this picture here, the thing that's parallel is that difference. Yeah. Is that so? Everybody happy with that? It's an easy, common source of confusion. Yeah. Okay. All right. Okay. So different form of the equation. Sometimes you want a coordinate equation. Boom. Sometimes you want a vector equation. If you're going to do vector algebra, you want the vector equation. One of these vector equations. Okay. All right, so a really nice takeaway of this, though, is that if you get a coordinate equation, like so, now this is, sure, that's the equation of a plane, fine. There is free information looking right at you in this coordinate equation, right? And that is that these coefficients, A, B, C, those coefficients, those are telling you the coefficients of your normal vector. That's what your normal vector is. You can read it straight off of the coordinate equation. Does everybody see what I mean there? It's kind of a neat observation. You might say that's where the A, B, and C came from in the first place. And so I can think of them as telling me, by working backwards, effectively telling me what that normal vector is. Okay. All right. Okay, let's do an example. This is one example of countless in a certain category that I like to think of as puzzles. All of the puzzles that you would encounter in this sort of category, this section of the book, certain things are going to be given, and then certain things you're going to want to find. Now, in this case, we're given 3 points in a plane. What we want is to find the equation of that plane. How would I find that equation? There's other kind of analogous. Maybe I'm given a point and a line, and I want to find the equation of the plane that contains both of them. Maybe I'm given 2 points and another line, and I want to find the equation of the plane that contains the 2 points and is parallel to that third line. Or maybe I'm given 2 planes and I want to look at their intersection, and oh my gosh, there's a bazillion different such questions of this same kind of category. Does everybody see what I mean? So I don't want to focus on how to solve this particular puzzle. I guess so. I'll talk through all these details, but try not to get lost in the details of how we solve this particular puzzle. The big takeaway here is, what is a strategy for solving these puzzles in general, right? And here's the big picture of this sort of strategy for how to solve these puzzles. Be very clear in your mind of what you are given and what you want. And then from what you were given, try to reason forward a little bit. Don't worry about making it all the way over to what you want. Maybe you will, maybe you won't, but don't sweat it. Work forward a little and just see what else you can get out of what you have. And then also look at what you want and kind of try to reverse engineer and work backwards from that. So starting with these as givens and this is my goal, if you work forward from the givens and backwards from the goal, you might just meet up in the middle. Very often that will work. And you just got to think about, what are the tools that I have and what do they do and what do they allow me to conclude, and see what you can do. So here we go. Let's see here. Let's start with the givens. I was given these 3 points. What can I do with points? Not much, I suppose, but I can subtract one from another. And geometric facts about subtracting points, that difference, C minus A, is parallel to the plane. Now, so I started with something I was given. I've moved a little bit. I've constructed something else. Is that going to be useful? Well, we'll see. And then likewise, of course, I can do that with A and B as well. And I have now 2 vectors parallel to the plane. Okay, fine. Now let's work backward from the goal. My goal, again, is to find the equation of the plane. But wait a minute, how do I find an equation of a plane? Here's my goal, my equation of a plane. What is it that I would need to make that equation? What comes before concluding what the equation is? Well, let's see here. How do I make the equation of a plane? Apparently, I need a point in the plane and a vector perpendicular to the plane. Well, the point I've got 3 of them. Take your pick. A, B, C, doesn't matter. Suit yourself. What I don't have, therefore what I need, is a vector perpendicular to the plane. So here's kind of what I need. I need that perpendicular vector. Okay, so again, don't think of this at now that we've worked a little forward from our givens, we've worked a little back from our goal. I no longer have to view this as I was given 3 points and I want to find an equation. I can view this now as I have 2 vectors parallel to the plane and I want to find a vector perpendicular to the plane. Everybody see strategically, I've kind of worked toward the middle from both sides, and I have a relatively easy geometry problem now. How is it that I take two parallel vectors to the plane and generate something perpendicular to the plane, and the cross product is exactly the tool for that job. Everybody good? Okay. So again, that's the specifics of this exercise, but try not to get lost in the specifics. The point here is that there's a bazillion different givens that might come up in some example, and there's a bazillion different goals that you might be trying to get to, and be clear about what they are and try to meet in the middle in whatever way you can. Okay. All right. Okay, let's see here. Oh, I can't see. There we go. Okay, so moving along. This is a cool fact. This is actually a really cool fact. This is an observation that will cost you nothing but a glance. And at the cost of that one glance, you can draw a really powerful conclusion about the equation of a plane. Now, so this is just kind of keep one eye open for this. Here it is. If you look at the equation of a plane, and if there are no y's in the equation, such as, for example, check it out, no y's in that equation, right? AX, 0 y's. And then some z's, etc. If that happens, so easy to observe. Just look for the absence of y's. Costs you nothing, and the wonderful conclusion is that plane must be parallel to the y-axis. That's a significant geometric conclusion that you get for noticing something. No calculations necessary. Yeah.
Previous question, I don't know if I understood it wrong, but you said we need to form the plane's equation, we need a normal vector, so a vector that will be perpendicular to the plane, and also a point inside the plane.
Yep.
But the equation that we just saw in the last example, we don't really use a point. We're just using the coordinates of the normal vector. So why exactly do we need a point inside the plane?
So are we still talking about this example? I'm sorry, I just didn't quite understand.
No, like the last example.
Back to here?
Yeah, so here, we're not really using any points in the plane. We're just using the coordinates of the normal vector.
Yeah. No, okay, I gotcha. So what I'm doing is I'm using this alternative form of the equation for a plane. So there is, in some sense, I'd kind of have to know a point in the plane, but it's hidden inside of this D. Right? If you go back up here to how we related this vector equation to this coordinate equation, where this D comes from. It comes from the x naught. Yeah. So, in fact, if you technically you don't really even quite need the x naught. All you really need is the x naught's dot product with the normal vector. So, just knowing the right hand side is good enough. Okay. Yeah. All right. Good. Okay. So let's talk through why this is true. Let's see here. So, here's our equation. Again, no y's. Cool fact from the previous page is that these coefficients tell me my normal vector. Gotta love it. Okay, well, I could draw a picture of that normal vector. Here it is. And keep in mind, that's perpendicular to the plane. But a real easy observation I can make, that normal vector is pretty evidently perpendicular to the y-axis. In particular, let me just look at the vector E2, J if you prefer, 0, 1, 0, and it's pretty immediately clear that this dot product is 0. Now, if this dot product is 0, that means the green vector and the purple vector are perpendicular. And now, geometric appeal. the plane is perpendicular to the green vector. The green vector is perpendicular to the purple vector. Knee bone's connected to the leg bone and all that. And that means this plane, just a geometric appeal. Look at the picture. The plane has to be parallel then to the y-axis. Everybody buy it? Now, that is an appeal. That's a geometric appeal. I hope that is geometrically satisfying. I'll have more to say about that on Friday, but we're out of time now. So we're going to draw the line right here, and I'll pick up there on Friday. Y'all have a good rest of your week. See you Friday.